All right, those that were absent and anyone that might want to relook at the notes if I go too fast, which really shouldn't be the case, but I had them read and then follow these directions. So stop the video and try to do that if you want to own your own education, so on and so forth. Okay, you're back. All right, so then the next thing I showed was this. This is from reading those directions what you should have drawn. Okay, from one and only one vertex that you pick, draw all the amount of diagonals that you could. Super fast, quadrilateral, I can draw only one diagonal from of any particular vertex that I choose from, which creates two triangles. Pentagon, pick any of these. Move this over here. Any of these vertices. I decided to pick this one. I could draw two diagonals, which creates three triangles. Any of these, I picked this one. 1, 2, 3 diagonals can be drawn. 1, 2, 3, 4 triangles are created. So we know a triangle has 180 degrees for their angle measures all added together. We know a quadrilateral has 360. Well, as we keep moving on, this is why the interior angles sum keeps going up by 180 because the amount of triangles that can be drawn from the drawing. So here is that extrapolation, as this doesn't let me move. Love my computer. That's your number 2 in the notes. I did some adjustments from old ones. But the sum of the interior is the number of sides of each polygon increased by 1. The angles add up to 180 more because you're adding a triangle. Oh, and I just realized I didn't put the good microphone in. Okay, shouldn't have shown you that, but then the next thing I had class do was fill in that chart on their own and then shared those names that we should know. So we should know those names. Heptagon 7, octagon 8. This is a weird one, nonagon. And then not listed in the chart, but decagon, unagon, another hard one, 11-sided, and dodecagon. I believe there are names for these other ones, but then we just kind of give up on the names and say 13gon, 14gon, 15gon, and so on and so forth when the numbers get moving up. Okay, so kind of caught up, even though that was quick because I forgot to do the notes video when I started. Sorry about the bad sound. Okay. All right, so now we're back, and my mouse is acting like a jerk. Now, there we go. Okay, so here's where you should have had for this. If a polygon has 100 sides, how many triangles are formed? 98. That's 2 minus. All right. And then what is the sum of those interior angles? Whatever 98 times 180 is. So the calculations aren't that bad. Can't really make anything big and extravagant over this stuff. So it really isn't that bad. What you should have had next is, if a polygon has n sides, how many triangles are formed? N minus 2. 2 less than the amount of sides that you have. There's an expression. Now, a rule for any sided figure. Then the sum of the interior angles, that's how many triangles you have. Each triangle has a sum of 180. So it's 180 times n minus 2. That's why I highlighted this as your formula that you should have for this. So I'm just going to write these in and then just kind of show you what you should do for 9 being in an honors math 2 class. I do expect speed. I do expect you to do things quickly. All right. So that stuff is expected. Not a bad thing. But this would just be 3180s. And I do want to say this too, those that have a little bit of extra interest in math. This is actually, I told you about that history of pi book, and then I've actually heard this in other things. As you increase the number of sides of a polygon, what does that polygon start approaching to become? Like, say you have a 100-sided polygon. What might that look like to you, actually? Yeah, a circle. So actually, we're going to do area next. And the more sides that you add to a polygon, the area of that polygon becomes closer and closer to equaling the circle that polygon is inscribed in. That should be a thing that you remember, that word. So if I put the polygon in a circle, as I increase the amount of sides in that polygon, it becomes more and more like a circle. You can calculate the area of a polygon through a formula very easily. And then that's how the relationship between area of a circle and pi got discovered. And that was another epiphany for the ancient people, I guess you want to call them. All right, so some of the interior is 1580, 9540. I mean, I don't know where 1580 come from. How many sides does that polygon have? Well, you use that formula. This is the sum of all formula, and the sum is 9540. So our newly found formula, we set those two equal and we solve. The very first thing you should do is divide by 180. Boy, I'm going off of memory. Anyone do this? Anyone set this up? Is it 53? Is my mind correct? Okay, so then it's not a 53. And by the way, what can't this number be? It starts with a D. 3, 2, 1, go. Decimal. Because you're trying to get an exact amount of sides that this should equal. So if it was a decimal, either you made a mistake or I made a mistake. I meant to write 9540 and I wrote 9450. Yeah, everyone has I think a little dyslexia. Sometimes I do the old switcheroo when I'm typing. I was typing yesterday and I switched a lot of my letters as it was 12:30 at night, trying to get this notes together for you here. So it's a 55 gon. You add 2 and you go from there. Again, when I make the notes, I have the idea, boy, I'd like to get all these examples in. I'm just going to skip to 9. Here's what I mean about what you should do fast. You should go ahead and take these 3 and add them as like terms right now. So 34 plus 16 is 50 plus 24, is that 74x? Is that correct? You should see how hard it is to write. You may think I have like some sort of problem with my hand. This is literally like writing on an ice cube. It's like it's like writing on a skating rink. I don't know how else to tell you. I used to have students write on my screen, and they take care of the notes. That's not what happened. And then you'd see how annoying it is to write on this computer. And all right. And then did you add those 4 blue ones? Did anyone do that? I think it was in the 500s from last hour. Is that correct? 530. That sounds familiar from last hour. And then, but what should that equal? Well, we got to count 1, 2, 3, 4, 5, 6, 7. So it's a heptagon. I didn't spit on any students on that one. So it's 7 minus 2, which is 5 180s. That's what this sum should end up becoming. That's what we're getting to here. This is the formula that you need to understand. Okay, I guess I could write 7 minus 2 times 180, where that 5 came from. All right, and then I'm not helping you solve a 2-step equation. If you can't do that, this is why the class is a problem. All right, so let's move on. And if you remember, you probably don't, I kept trying to use the word regular for average quadrilaterals, and that is completely incorrect because a regular polygon is actually very specific. By the way, I have a question. What is a regular quadrilateral? Are you listening over there? What is a regular quadrilateral? Raise your hand. Which one specifically is a regular quadrilateral? I already got an answer. It's a square. There's only one answer for that. Because a regular quadrilateral, what's the quadrilateral with equal sides? Well, square or rhombus, but then with equal angles. Well, now we're only a square. All right, so a regular quadrilateral is a square. All right, but a regular polygon is where all the sides are congruent and all the angles are congruent. So now what we can do is if I have a regular triangle, that's an equiangular triangle. So 180 divided by 3 is 60. We know that. And then we know a quadrilateral adds up to 360. And we know that each angle then would be 90. There's the square. I know a rectangle has that as well, but a rectangle doesn't have 4 equal sides. So that's why a square is what has to be in this little part. So then what you got to do is if I have a regular pentagon, sure, they add up to 540. You can use your calculations from our previous charts. Oh, but I didn't fill those out because I cheated. I used Mr. Samuelis's notes from a while ago. And then you got to divide that by 5. What do we end up getting for that? 108. So every angle measures 108. Keep going. What was this, 720? What's 720 divided by 6? What is it? 120? Could have probably figured that one out. Then here's our only decimal. Add another 180. Isn't that 900? Right? And then what's 900 divided by 7? Wasn't it like 128.6.57, right? Okay, or 0.6. Pick an angle. And then add another 180. This is 1080. What's 1080 divided by 8? 1 what? 30 what? 5, okay. And it is not a decimal. It's perfectly on. Okay, so then this comes to this. And then wait till I show you how I can change number 6 and make it a little bit easier. For regular polygon has n sides, write the formula to calculate the measure of each interior angle. So that is the sum, sorry, that was me, sum of all divided by the amount of angles you have. This pen is just so gosh awful. All right, the sum of all is from our first formula, the amount of triangles you could have from the diagonal thing that we started with. There's n sides, there's n minus 2 triangles. For every triangle, it's 180 degrees of angle measure. Divided by the amount of angles is equal to the amount of sides. So it's divided by n. This is only if it's a regular polygon. I cannot overemphasize, this is obviously not a regular heptagon. There's no way at all. Look at the sides are all weird, and all the angles are not equal. But it still has the same sum, 5 times 180, but every angle is different. When you have regular, then you can do this. This is for regular polygons only, all right, that we can divide by n to find each angle measure. So for what formula to calculate each interior? Again, 100-sided polygon. If you looked at that from far away, it would look like a circle. It's almost impossible to draw a 100-sided polygon. All right, but anyway, 100 minus 2, see my pen, times 180, but then divided by 100. And that's what each angle measure would be. Who did that? What do we end up getting? It should be, what is it? 76.4. Is that correct? Would you agree with that? 176.4. Yeah, because think about it. It's almost like you're getting so big on this angle measure. It's almost 180 degrees, right? All right, so here we go. If each interior angle measure of regular polygon is 150, wait till you see the next page what I'm going to do with this, all right? But we're going to set this up. Determine the number of sides. So that's each. Again, this comes from reading, and this is where we didn't really read in the beginning if we didn't do our first thing correctly. So again, it's you better make sure you read, all right? So each is 150. So all times n minus 2 divided by the amount of angles you have. That's what each is from our formula. And then that equals 150, because that's what each one is. 150 degrees. This is the formula for each. This is what each is given as. What should I do first in order to solve for this? Multiply both sides by what? N or cross multiply. Make this 150 over n. All right, and then I'm just going to treat this as the note time as we have 15 minutes left in another concept. Distribute as well. This one I will go ahead and solve just out of curiosity what the answer is. Then you should be able to do two things in a one-step, two-step solving of an equation. And again, if you're still struggling on this, this is not my fault, all right? Because this is where we have some people that are still very sloppy with their math and don't solve these two-steppers very well. All right, so subtract 150n, that gets me 30n, add 360 to both sides, and then n equals, I can't think. So is that 12? Is that 12? What is that called, by the way? Someone said 12 gone. You're gone. I'm going to get you. Right? Now you have up to 12. What is it called? Dodecagon. There it is. It's all gone. All right. Now, go ahead and I'll give you a minute to follow the directions on this page, and I'll walk around and I'll pause the video. Okay, so follow the directions on this one. All right, and then I'm going to go ahead and show you completed when I'm done, and I got to pause this. So how do I do this again? Ay, caramba. Oh, there we go. Nice. Start and stop. I know I'm going to screw that up one time. All right, going to cheat. Bum, 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 Samulus. Boom. This is what we should have got. Okay, every single time. Frozen. Let it go. Not on the video, but on my screen here. 360. This is what should have happened, and this is what you should have done following directions. This guy right here, Ryan, did exactly what I figured out as well to do on this one. I love his whole thing where, okay, we have a regular hexagon, so 6-sided, 6 minus 2 is 4, 4 times 180 divided by 6. Each one of these is 120, so each of these exteriors is 60. So 60 times 6, there we go again. We got a sum that equals 360 on the outside. You don't have to do this way, but it's either one way or the other. I either extend this way or I extend this way to show the exterior angles. That's what ends up happening. So this is not a formula. This is an actual, it doesn't matter how big or how many sides. And it doesn't matter if it's a regular polygon or not a regular polygon. This holds true always. So 100-sided, the exterior angles will add up to 360. N-sided, it doesn't matter. It's not a formula. It's 360, right on the dot. Okay, and then I'm going to show you something here, but just, real quick on this then, picking one of the two again, I, overzealous on maybe how many examples. Don't really need two of these. These are exterior angles. So add the x's together, add the constants together, not a formula. Those should equal 360 in all cases. All right, so two concepts, the idea of interior and the idea of exterior. Now I'm going to show you something, and it's actually in this chart. Go ahead. Now we only have 5 minutes, but this is what you were supposed to be doing in your 5 minutes, and this is what I wanted you to understand. Listen. I'll say it one more time for those that don't listen. Listen. There's now a little bit easier way to tackle even when you're given an interior angle. So let's look at this chart. Of course, for a triangle, the exterior angles add up to 360. Divide by 3. We saw that literally on the drawing up there. Each exterior was 120. But now, what's the relationship between an exterior and interior? Let's look at these. What would be the word that describes the relationship between these two? Starts with an S. 3, 2, 1, go. Supplementary, that happens after. That's a question later after this chart. So notice when I know, again, listen, this is only when you have a regular polygon in this chart. So focus on that word regular again. I threw a regular word on this after the extrapolation. If it is a regular polygon, each exterior is 120. That makes each interior 60. We know that. 60, 60, 60. We know that 90, 90, 90, 90 is squares for angle measures, right? But the exteriors are also 90 because they add up to 360. Now notice how this chart works. For a pentagon, the exterior angles are 360. Divide that by 5, you get 72. From this, we could find what the measure of each interior angle is then from the exteriors. All right, and that's the point of this chart. We got this one for heptagon. Well, let's look at 360 divided by 7. You get 51.4 supplement, 128.6. 15gon, I think that was in our earlier thing. So let's go back up to 6. This question where I had this set up here. And I told you, the regular Math 2 students had a hard time figuring out how to solve this equation. So guess what? if each interior angle is 150, what is each exterior angle, everybody? 3, 2, 1, go. 30. So really you could get the same answer with 360 divided by 30, which is equal to 12. So that's what I tell my, honor students. Hey, if they give you an interior angle, find the corresponding exterior angles measure, and then just divide that by 360, or take 360 divided by that. I said that wrong. Okay, I wanted to reverse that mathematically. Okay, so in our time that we have together here, just showing the rest of this, that's what's going on here. This number 6 corresponds with the number 6 that I had, before. This time, though, they give you the exterior angle is 18 degrees. Well, each exterior angle is 18 degrees, and they add up to 360 total, so just divide the two, and you get a 20 gon. 20 gon does have a name. Should end the class with searching that on Google to see what a 20 gon is called. Well, let's do that out of curiosity. What do I have opened? Hopefully it's okay. So let's do this. No, it always says, let's put it up here. 20 gon. Let's see if there is a word for this. Google's awesome for this. 20 gon. Well, there it is. Icosagon. I should put that in our terms. You can play this. You can do this all day long. You can type in different gons. I'm going to put 100 gon in there. Of course, Google never lies. You can always trust the internet and the news. Oh, it doesn't say a word for that. I'm very disappointed. Oh, what is the name of this polygon? Oh, bummer. It doesn't say 100 gon. Let's say name. Oh, there we go. I think there is a name for this. Why am I doing this? Whoa. Did you see that? So hectagon, hectagon. I don't like that. All right, so I told you there was more names. It's just very hard to remember all of those. Okay, I'm done.